Hi everyone, welcome again. Our next speaker is Kiera Kean. She's from University of Pittsburgh. Kiera, you can go ahead.
Sorry, can everyone see this all right?
Yeah.
Okay, so I will be presenting work, as you said, on the Prandtl-Kolmogorov one equation model for turbulence, which is work that I did with my advisor, Dr. Layton, and with Dr. Michael Schneier. Turbulence is, of course, very observable as a phenomenon, but mathematically it remains an incredibly difficult problem, and numerically fully resolving turbulent flows on a large scale can be considered to be somewhat impossible with current computational limitations. As the Reynolds number increases, the smallest scales that we need to resolve gets scale inverse the Reynolds number, as do the smallest time scales. So we need to take incredibly small time steps and incredibly fine mesh to fully resolve these flows, which again, with computational resources is impossible for very high Reynolds number flows that are relevant in many applications. So pictured here are two direct numerical simulations of turbulent flows, both shear flows, a jet entering a tank, and cross sections of Taylor-Couette flow, which I'll discuss more later. We can do this for smaller problems, but again, for larger problems, we look for turbulence models. So we will truncate the scales that we directly calculate and model the effects of the unresolved scales. A lot of turbulence models are somewhat ad hoc and maybe not supported mathematically. So we want to make sure that when we're using or creating a turbulence model that we're actually capturing what we need to capture and preserving what we need to preserve. So for example, the rate of energy dissipation and the long time average will match the rate of energy input. So energy U squared over time should be equal to U cubed over L, where U is the global velocity scale that we would use to define the Reynolds number. So something like the velocity of the jet entering the tank, or the velocity of a plane in application, or some time space averaged velocity. And L is, again, the global length scale. So the width of our domain, the length of an airplane, the width of a pipe or something. And this should be uniform in the Reynolds number. However, a lot of models will fail due to over dissipation, so this is not preserved. So what I mean by this is kind of the behavior we should see. Drag is a kind of something that we can measure easily in a laboratory. So this is results of drag versus Reynolds number from actual experiments. And we see that as the Reynolds number increases, we approach a constant, which is kind of what we would expect from, but over dissipation, it would be if the drag were to increase as the Reynolds number increases. And again, this is not physically accurate. This here is a drag crisis, and it kind of, I guess, looks like it decreased, but the drag, there's both pressure drag and the drag of the wake behind the object, and when the wake detaches, this drops off. But the important thing to see is that this will approach a constant in reality. When we're going to like take a step back and kind of look at how we would actually derive these models. So we have the Navier-Stokes equations in the incompressible case here. That's equation 1, and we take the average, currently just a generic averaging operator, which will commute with derivatives. The only place where we have something different is in our nonlinear term. So when we decompose our velocity into means and fluctuations, we get this additional term in red on the bottom here, the Reynolds stresses, which is the effect of the fluctuations on the mean flow, and that is what we need to model. So we'll be considering eddy viscosity Urans models. So the averaging would be a finite time average, and V approximates this average. We average backwards in time to preserve causality. If we're averaging the force, it's important that the future behavior not affect the current velocity. And we model the Reynolds stresses with enhanced viscosity. So the Reynolds stresses in the long time average have been proven to be dissipative. So by adding this additional dissipation, we model their effects. And the formula for nu-T, this turbulent viscosity, is given by Kolmogorov and Prandtl. So there are different ways to determine L and K. L is analogous to the mean free pass for molecules somewhat, but for eddies. And K is how we model the kinetic energy in the turbulent fluctuations U prime. So zero equation models, we can get K and L from data fitting. So that would be something like Smagorinsky or Baldwin-Lomax. And we do see with Smagorinsky, particularly in the presence of boundary layers, that this will over dissipate and drive our model to lower Reynolds number states. One equation models, K is determined by the K equation. Again, this was given by Prandtl and Kolmogorov, but there is not a universal specification for L. So there's we need some other formula or way to get that. We also have two equation models. So that would be the K epsilon or the K omega models. There are others as well. They can yield poor results, and they're significantly more expensive computationally. And so we'll be focusing on the one equation model, which is given here. So we have the V equation. Again, this models our average velocity. And then we have the K equation, which gives us our kinetic energy in the our turbulent kinetic energy. And then we still, as I said, need to find a way to choose L. So two common or methods for choosing L given by Prandtl. So we could consider this length to be the diameter of a mass of fluid, and take L is equal to 0.41 D, 0.41 being the von Karman constant, which comes from data, and D being the wall normal distance. We could also consider this kinematic length scale, where L is the distance eddy travels in one time unit. So if we take U prime as our velocity and tau or as our time scale, we can solve for L this way. So in our paper, we looked at a different length scale, which is the minimum of these two quantities. Away from the wall, we use the kinematic length scale, which was proven to not over dissipate in the periodic case. So away from boundaries, this method is not over dissipative. And near the walls, we use this D to the 3/2. And again, L is a constant, the one that we saw before. So this is dimensionally consistent as we have the square root L, and will more correctly model the true near wall behavior. So to kind of get into that further, we have K true, which is the true kinetic energy in the fluctuations, which we do not know, of course. But what we have is K, the solution to the K equations, and they're not equal. So Reynolds stresses, which is what we're approximating, are order d squared near the wall. But the K equation, our boundary conditions don't give us any information about K's derivatives. It does not go to 0 at the wall like d squared. At best we have order d, or couldn't expect more than that. So if L is order d, then nu t, which should be order d squared, will be d to the 3/2. L order d, d to the 3/2, and we should see that nu t will be order d squared. So this is more physically accurate, and our hope is would be that this would reflect in capturing this accurate long time energy dissipation. So we look at the problem in the shear flow case. As we said, we're interested in what happens in the presence of boundary layers. So we take a box plus length L. The top of the box moves in the x direction with a velocity u. The bottom of the box is fixed. And we have periodic sides in the x and y directions. For the K equation, we have 0 boundary conditions on the top and bottom. And the wall normal distance is just given as the minimum of the distance between the top and the bottom of the box. So we get our energy equation by, again, starting with the V equation and multiplying by W that has 0 boundary conditions in the Z direction, periodic in X and Y, divergence free. We don't have any force. This is just a boundary different flow. So F would be 0 in this case. And this is our denoting the standard L2 inner product. As is typical, we can move the boundary conditions to the right-hand side by taking phi, which will satisfy our boundary conditions, be divergence free, and test with W equals V minus phi. And for choice of phi, we use HOP. So this is divergence free and satisfies the boundary conditions. As I said, that's necessary. We want it to be constant except for near the boundary, and linear when it's not constant. We could also choose a function that's symmetric and has this, I don't know if you can see my mouse, but this approximate shape. So we have boundary layers on both sides, but that will, in our analysis, just change some constants. So this is simpler. We'll consider this case where we have a boundary layer of beta thickness space. So this choice of background flow function is necessary. Using just the most obvious choice of a linear and turbulent from 0 to L will not work. So in the paper, we did prove all these uniform bounds on the finite and infinite time average. But again, not the interesting or important part, so I will refer you there if you're interested in those details. We also define the following quantities. So we have the boundary region. This is the strip beta thickness, and it is where the function phi is supported. We also have the effective viscosity and the effective Reynolds number, which are relatively commonly used concepts in turbulence modeling. Our new term that we define is the average viscosity, which is, as it sounds, the average of the viscosity in the boundary layer specifically. And we also have our energy dissipation rate to be a combination of viscous dissipation and model dissipation coming from our enhanced turbulence viscosity. So we can start by looking at the most general settings. So not examining any specific turbulence model, we look at this bound. So basically what we have here is that we should see the correct energy dissipation rate if we can control nu bar over nu effective. So the ratio of the average to effective viscosity. And basically we would expect this to be well controlled if the viscosity is not much larger in the boundary layer, but we'll kind of get into that more later. In terms of the analysis, it's always a little difficult to do a proof in a PowerPoint. So most of the terms, we will just follow the analysis done by Constantine and Doring, as well as Xiaoming Wang. And we'll kind of mostly just go into the details of the differences in what we did versus what was done previously. So we start with the energy, and we'll average in space and in time. So finite time average for now. And then we'll compare the analysis to the analysis in the Navier-Stokes, as I said. So this term, due to uniform bounds, these terms in green are order 1 over t. So in the infinite time average, they will drop out. This is the term that we're looking to bound in blue. This term in purple is where we'll see something different from the Navier-Stokes case. And this term in red is virtually identical. However, we have the nu effective here from multiplying and dividing. In the Navier-Stokes case, we just multiply and divide by nu. So again, the purple is the term that we'll actually look at. So what we do here is the key is we restrict to the strip where phi is supported. And then we can apply Cauchy-Schwarz in space and time, extend back to the whole domain to have our energy dissipation rate, and then use the definition of phi that we had earlier, and then just rearrange terms to get this final result. We can put it all together. And then when we take the infinite time average, this term here becomes nu bar. in the average viscosity in the boundary layer. And this term, by how we define the effective viscosity, becomes just our energy dissipation rate. So beta is something we can select. So if we make this choice of beta, the result follows. So we see this our purple term, and then this just becomes, again, energy dissipation. So kind of putting it all together, we have the result stated before. Again, this is not model specific, and for any model, if you want to see if it will over dissipate, you look to estimate nu bar over nu effective. Returning to our model, we defined T star as a large eddy turnover time, and consider our choice of L. It's maybe looks a bit of a mess, but nu over nu effective will be less than 1, and in many cases maybe much less than 1, as we would expect that if our effective viscosity was approximately equal to our viscosity, our turbulence model isn't really doing anything. And this is a mess of constants that is about equal to 0.017, so not very large. Again, I don't want to go through every single detail. It's available in the paper, but the key is that we use this estimate in the boundary, and then this estimate in to, again, bound the long time kinetic energy average. So again, the basic details is we have nu bar and nu T. This can be, again, restricted. And then we have this definition, of course, for nu bar, for nu T. And then just kind of plugging in all our terms, we can have this in terms of K. So this is what we need to bound, which we then go and use the other bound on L to do. So if we take the long time space average of the K equation, some terms drop out. This is equal to 0 by the uniform bound on K. And then we have, I can bound this term below and this term above. So kind of have, this is our final result. Or I say final, and then, plug it back in. Decent bit of rearranging, arithmetic geometric mean, and we have the final result for real this time. So we also did numerical tests. So we looked at flow between counter-rotating cylinders, which I have a video of. This is not a test that we did, but it's a fairly common experiment that one can do. So we have, again, counter-rotating cylinders, a fluid inside, and by varying the speed, we can see sort of different patterns start to appear. So the Taylor vortex is kind of the characteristic just bands of vortices, and as we spin it faster, we see wavy Taylor vortex flow, and as we continue to speed it up, we would see turbulence, but not pictured here. So we also have kind of the Taylor number, which is analogous to the Reynolds number, which is defines kind of what the flow looks like. So we did all of our calculations in Phoenix. The code is actually available on my GitHub if you're interested. We varied the viscosity to vary the Reynolds Taylor number, and we fixed with a fixed rotation speed, angular velocity. So we took periodic boundary conditions in the z direction, so we didn't have to take a very long cylinder, as one often might in these numerical tests. And We benchmarked our code with the laminar solution to Taylor-Couette flow, and we saw agreement. We also saw when we plotted the Q criterion that we, in the lower Taylor number, more viscous simulations, we see this, again, characteristic Taylor vortex, and we see the wavy Taylor vortex as we increase the Reynolds or Taylor number. The Q criterion is a way to mark the coherent structures. So it's the difference between the skew symmetric part and the symmetric part of the gradient of the velocity. And we saw that, or this is also the spin and the deformation tensor. So when it's kind of holding together in a vortex more than it's being pulled apart, and that's pictured here. We also showed in numerical tests the behavior we'd expect, which is a constant plus this Reynolds number to the -1. This agreed with theory almost exactly, and we were very pleased with our results, though we were somewhat limited in how high we could take the Reynolds number. But again, overall, with the proposed choice of L, we did show that the energy dissipation rate did have this U-cubed overall we would expect, and that the energy dissipation rate did not increase as the Reynolds number increased, as which we saw supported in our numerical tests. Again, there's the paper and another related work. Does anyone have any questions?
Thank you, Kiera.
Yeah, no problem.